And you'll want to, click back onto the other thing.
But this is
Okay, so thanks everyone for coming. Sorry about the delay there. The speaker today is Hanwool, who's visiting from the Korean Astronomy and Space Sciences Institute. Hanwool's doing his PhD, and he's going to tell us about the research he's been doing. Please take it away.
Hi everyone, I'm Hanwool, PhD candidate in the final year in Korea Astronomy and Space Science Institute at University of Science and Technology in South Korea. So I'm working with my supervisor, Professor Arman Shaffield, in the same institute, and I'm going to give a presentation about my research work, my collaborator, in the title of Cosmology with Method of Victorious Moon. So for more detail, please see the papers on the slide, and you can also ask questions at the end of the presentation. So before I start, here's a brief introduction about backgrounds on type supernova cosmology. So type 1 supernova is used as a standardizable candle for distance measurement and have become one of the important portion of modern cosmology. So it's well known as the source of discovery of accelerating universe, and also has many important roles in cosmology. And there have been many compilations of type SN1A from the first supernova cosmology project, and and I have worked on recent compilations, including joint light curve analysis, and now I'm working on Pantheon Plus, but I'm going to show the results from the less recent one, the JLM and Pantheon, and then I expect more compilations from forthcoming surveys, including DESI, LSST, and Roman. So I already mentioned that type 1 supernova is used as the standardizable candle, but the standardization of this type 1 supernova is purely empirical and usually based on assumption of cosmological model. So I would say it requires modern independent analysis for standardization. More in detail, the constraining type 1 supernova like hyperparameters need to be done in modern independent way. And this modern independent analysis also required for systematics for features in the data, model selection, parameter estimation, and so on. So I'm going to show you how to use the method I'm going to introduce for constraining type 1 supernova like hyperparameters in modern independent way, and then how to apply the method for model selection. And before going there, I'm going to show you one example that using the type 1 supernova data without using the modern independent analysis. So here's an example of looking at the type 1 supernova data. So it shows so this table shows oscillatory features in the Pantheon data around the best fit lambda CDM. You can see so there are two parameters, and you can see the best fit values of the two parameters, which are absolute peak magnitude and the matter density at present time. The top one is for the full data of Pantheon and Pantheon compilation, and next to that there are 4 different reshifts within the Pantheon. So these reshifts all have the same number of data points, but the sizes are different. So you can see that the best fit values for redshift bits are different with the best fit value from the full data, and you can see that the first redshift bin, which is the lowest redshift bin with lowest redshifts, have the best fit value lower than the best fit from the full data, and then the second redshift bin have the higher value, and then the third bin have the lower value, and the fourth bin shows So this is what I call oscillatory feature in the Pantheon data. And what I worked on is, without model independent reconstruction, is I checked in how many cases these oscillatory features occur in the Pantheon-like simulation. So I generated 1,000 Pantheon-like simulations and checked if such oscillatory feature occurs. And I found that in 4 to 5% of cases, this, such oscillatory feature occurs at redshift lower than 0.5. And I think this might be a hint to possible systematic order. So this is just an example without modern without using the type 1 supernova data without modern reconstruction. And then now I'm going to introduce the method for reconstructing the distance, reconstructing the expansion history of the universe in modern dependent way. So this method is called iterative smoothing method. This method is the non-parametric method to reconstruct the expansion history of the universe, basically. But this can be changed to the form of observable. So for the case of type 1 supernova data, it can be changed into distance models so that this method can reconstruct the distance models as a result. And this method has been introduced by Shapiro et al. In 2006 for the first time, and then improved by many continuing research works. So this method can reconstruct the expansion history and reach to the model dependent reconstruction by starting from initial guess of distance model. So this distance models can be changed to different observable for different kind of data. But for type 1 supernova, this is so in this case, this is distance model. So it starts from initial guess of distance modules based on assuming a cosmological model, and then if I perform this smoothing method iteratively, it converges to model dependent reconstruction with, and the number of iterations should be high enough. So I'll tell you in detail. So you can see the equations on below, and that's the equation for this smoothing each iteration. So okay, by using the data points and covariance matrix of the data and the filter for performing the smoothing, it can move on to the next iteration with the reconstruction, which have lower chi-square value and becoming model dependent. So if you see the figure on the right, you can see the dashed line, which shows the initial guess. So this initial guess can be different, can be any kind of assumed model. But here, this shows the non-Euclidean band split, but this is just as an example. So from this initial guess, if I perform this, if I use this equation, perform this calculation iteratively, it moves to the blue line on the top. So that's the final reconstruction. And there are many reconstructions with less number of iterations between these two lines. So from that dashed line to the blue line, there are many light blue lines, and that's how the reconstruction and the iterations goes. So by performing this, the smoothing iteratively, it reaches to the model dependent reconstruction. So with the converged value of chi-square. So this is how iterative smoothing method works, and by doing this iteratively and using the final reconstruction, I can apply this final reconstruction to many different research works in cosmology. So there can be many applications, but first I'm going to show how to use this method for constraining the LiPo hyperparameters. I mean, the type 1 is SN1A LiPo hyperparameters. To show that, I use the joint light curve analysis computation, which have light curve parameters information based on south. And to construct the distance modules from the light curve information shown on the middle of the slide. So there are many parameters on the formula. Then small MB star, large X1, C are LICO information. So these are information from the computation. But there are still other other parameters, which are alpha, beta, large MB1, and delta. So alpha and beta are proportional factors to large X1 and C. And large MB1 and delta M are hyperparameters, which are for deriving the absolute peak magnitude. So these four parameters are like hyperparameters, and that's the compilation have no direct information of these hyperparameters. These hyperparameters should be constrained based on the information, and that usually happen. That usually have done and been done by based on certain model assumption. But
Are these the stretch and color parameters, alpha and beta? that what they are?
Yes, they are proportional. Yeah, so X1 and C are stretching and color information, and alpha and beta are proportional factors to those two. So I'm going to show how the constraints from the three different cosmological model assumption and the model independent reconstructions are different. So you can, and so I assume three different models on the CDM, simple parameterization of equation of state, and the other dark energy model, and I get the contours based on these three different assumptions. And yeah, you can see four different constraints for this. I like a hyperparameters. So you can see that the contours from three different model assumptions and model independent construction. So model independent reconstruction constraints are shown as red color, and you can see that they are all consistent with each other. There's only one exception. If you see the large MB1, you can see that the contour from reconstruction is actually not contour, it's just uniform distribution. It shows up because type 1 and supernova data alone cannot constrain the distance scale, because it's large MB1 is, in other words, this large MB1 is degenerate with the distance scale. So if I assume a model, then even this large MB1 can be constrained. But if from the model independent reconstruction, this one just shows uniform distribution. So this one will not be constrained from the model independent one. That's why it shows more. So except this one, all contours are consistent with each other. So between three different model assumptions and model independent reconstruction. So based on this, I can say that I find no dependence on cosmological model. So yeah, so before I show you this slide, I told you that I'll show you the difference between the three different assuming models and model independent construction. But in this, but as you can see, there is no difference, and that means there's no dependence on cosmological model. And then I divided the JLA data into two redshifts with equal sizes, and I showed the contours for the three hyperparameters, except the large MU, which show uniform distribution for the model independent reconstruction. So you can and these contours are all from model independent reconstruction, but use the different redshift beam of the data. So you can see that the contours from lower redshift bin and higher redshift bin show some deviation, but the deviation is within the 1 sigma or 2 sigma, which, so I would say the statistical deviations are not significant. So in other words, it shows no clear redshift evolution. So I have shown these pictures to show that by constraining hyperparameters using the model assumption and different model assumptions and model independent reconstruction, I found no. I conclude that there's no model. There's no dependence of these constraints on model assumptions and also show no clear ratio evolution. And then, so I have for getting this contours, I have used many model dependent reconstruction. And but here now, I'm going to use the same reconstruction for some use that reconstruction for different purpose. So here I'm going to use them for
Okay, carry on those.
okay, use them for exploring possibilities of the expansion history of the universe with higher likelihood than that of the lambda medium. To do this, I'm going to reconstruct the expansion history of the universe and dark energy properties. So additionally, on parametric space of like hyperparameters, and I compare them with prediction of the cosmological model. In this case, the lambda medium. So to do that, to get the contours I have shown in the previous slide, I have performed the MCMC analysis. And so there are like, so I get the set of hyperparameters. I got the different sets of hyperparameters, and then I got the contours from them. But now, I got from the reconstructions from those different set of hyperparameters. I'm going to choose on the reconstruction which have chi-square value lower than the chi-square value that corresponds to best fit to lambda CDM. So this is for like showing the possibilities which are higher likelihood than the lambda CDM using this model independent reconstruction. So you can see the red distribution on the left on the figure, and you can see the blue dashed line, maybe dotted line anyway. And so I chose only the red reconstruction which have chi-square value lower than that blue dashed. And I'm going to use them for showing the possibility around the lambda CDM. So this figure shows the reconstruction with only 1,000 number of iterations, but I chose reconstruction even with number of iterations lower than 1,000. And then I showed the reconstruction, and I'm going to show reconstruction of not only expansion history, but also deceleration parameter and the Ohm parameter. So this Ohm parameter was suggested by Shani, Shapiello, and Starovitsky in 2008. And this parameter is useful for like testing the lambda CDM because these parameters have the value of that this parameter equal to the matter density at present time, and with respect to redshift. When so for any redshift, it shows the matter the value of the matter density at present time when the assumed model is the lambda CDM model. So this Ohm parameter is useful for testing the lambda CDM model. But here I'm going to show how the reconstruction shows up around the lambda CDM prediction. So the lambda CDM prediction should be just simple uniform line, vertical line with the value of matter density at present time. But I'll show you the reconstruction around it. So I'm going to show reconstruction around these three expansion history, Ohm parameter, and deceleration parameter. And this is how they look like. So you can see many red lines, which are the reconstruction, which have lower chi-square value than the lambda CDM prediction. And you can see the blue lines, which are lambda CDM prediction. So, so you can see the red lines are like around the distributed around the lambda CDM prediction. And so from these pictures, I can say that this reconstruction in red are in good agreement with prediction of lambda CDM, but show considerable flexibility. I'm not saying they show inconsistency with the lambda CDM model because so if they have chi-square value lower than the lambda CDM. So they are showing the possibility. they are showing the possibilities which have a better likelihood than the lambda CDM. So their distribution does not show the inconsistency with the lambda CDM, but the flexibility around the lambda CDM. So if some of them are close to lambda CDM and still shows some deviation, that means they have some agreement, and they have an agreement with the lambda CDM prediction, but still have some flexibility, not inconsistent. So this, in this way, this iterative smoothing method can be used for showing possibility, exploring possibilities which have better likelihood than the assumed model. And these are the examples of how that works. And then I'll summarize this first part of my talk. And so first of all, I find that SN1A hyperparameter constraints for modern reconstruction are in good agreement with predictions of 3 different models, which means that I find no model dependence. And next to that, I find that standard deviations between the constraints from different redshift bins are not significant, and which indicate no clear redshift evolution. And then I've shown that reconstructed expansion history of the universe and the darkness properties are consistent with prediction of the standard lambda CDM model with considerable flexibility. And then I'll show you how I can use the iterative smoothing method for model selection. And also, I'm going to compare the model selection using this iterative smoothing method with the model selection using the conventional Bayesian approach. So before I move on, I need to mention that model selection using conventional Bayesian evidence approach relies on comparing models. But the novel frequencies approach using the iterative smoothing method, I would say based on iterative smoothing method, has consistency between a model and the data without comparing different. So the model selection method I'm going to introduce, which uses the iterative smoothing method, doesn't compare the model. So that's the one of the key difference with this model with the conventional Bayesian model selection. And so maybe someone might call it model validation rather than model selection, but I'll show you how it can be practically model selection. So first, I'll show you how I perform conventional. I mean the model selection in using conventional Bayesian algorithm. So I'm going to use Bayesian algorithm, which is the most popular way to perform model selection in Bayesian approach. So I calculate Bayesian evidence using the next template. So it's defined as integration of multiplication likelihood prior over the parameters. And then I calculate the ratio of the evidence of the 2 models, which is base vector. So I derive these values in logarithmic form, shown as delta log. So here, if this value is positive, so this base vector supports model 1 over model 2, and then I can interpret the value of base vector by using a scale. So this scale is not something absolute; it can vary, but I choose Cat-Raptor scale, which is one of the most popular scale for interpreting the base vector. And then this table shows how the scale looks like. So if the delta log Z value is between 3 and 5, it can be interpreted as strong evidence, which supports model 1. And then if delta log Z is larger than 5, it can be interpreted as very strong evidence. And then next to this, I'll show you how this novel frequency approach that I'm going to introduce works. So this method uses the statistic delta chi-square. So So to use this method for model selection, I should derive the distribution of the delta chi-square. I'll call it P delta chi-square for a large number of data realizations. So these data realizations are generated by using the covariance matrix of the original data, and by generating this realization for a large number, I can see the distribution of the delta chi-square. And delta chi-square is defined as chi-square smooth minus chi-square best fit. And chi-square smooth indicates chi-square of the converged reconstruction using the iterative smoothing method. And the chi-square best fit, it means best fit chi-square of the model being tested to the data. And the delta chi-square shows the difference between these two chi-square. In other words, it shows improvement of chi-square by the iterative smoothing. So the chi-square best fit corresponds to the case that the iterative smoothing method works on the initial guess or best fit of the model to the data. And that's why I say this delta chi-square is an improvement from the initial guess of best fit to the data of the model to the data, and to the converged reconstruction. So, and this delta chi-square can be used as statistic for performing model selection. So to show that this method works well for model selection, I'm going to calculate chi-square best fit, not a best fit chi-square of the model being tested, but the best fit chi-square of the correct model. So this means that I'm testing the model which is correct. But we don't know the true model in the universe. So what I'm going to do here, and what I'm doing here is selecting certain model as a fiducial model, and generates the data from that fiducial model, and test the fiducial model. But yeah, you can see many different distributions here. So which are the cases when the different models are assumed as a fiducial model. So, but still, and testing the fiducial model. So that's the same, but the fiducial models are different for this distribution. And you can see that the distribution from the different fiducial models are consistent with each other. This indicates that P delta chi-square have no dependence on the true model and depends only on the covariance matrix of the data. This is important because if the distribution dependency on the true model is not good for performing model selection. Only based on this, it can be a model selection. And then from this, practically identical distribution, I can get only one delta chi-square value for given confidence level. For example, this one shows 95 confidence level, and I can use this for model selection. I mean, selecting the candidate model, and I'll show you one example that this method that shows how this method works. So for doing that, I'm going to assume another cosmological model. So I'm using Langatilian Tele model again, but this time I'm going to choose the other model as fiducial model. So I'm going to choose transitional dark energy model as the fiducial model, and generate the generates the mock realization from that fiducial. And I'll perform two different model selection methods and compare the results. So you can see that these three models show different distinguishable equation of state. So the results, I chose this method intentionally to make the results, to make the distribution distinguishable. So then I generated 1,000 forecasted Roman, formerly known as W first type 1a supernova data, and with the fiducial TD. So in other words, I'm generating this mock realization using the Roman SM1A data covariance matrix, which is forecasted, and based on the PD model as a fiducial model. And what I'll do next is testing lambda TDM PD model. So these two models are different with each other, also different with the fiducial model. And I'm going to test these two models using the Bayesian evidence and the iterative method. So I should again note that this both candidates are different with the fiducial model, which is assumed as a true model for this case. So the result of this model selection should be both candidates are wrong. But I'll show you how the results are how the results are for these two different model selection methods. So for the first one, Bayesian evidence shows the distribution delta log Z as like this. So I used 1,000 log realization. That's why here's the distribution of delta log Z. So if you see this, you can see that in all of the cases, the delta log Z is larger than 1, which indicates the positive evidence for all cases. And for 99.4% of cases, it shows strong evidence, and 91.1% of cases shows very strong evidence. So I can say that Bayesian evidence, model selection using Bayesian evidence supports some of the teaching model. For this example, in this example, and don't forget I chose the certain fiducial model. So I'm really testing the TDM model with the real data. I'm just selecting one model as a true model and seeing that and showing that this method supports the TDM model. And so I have done this analysis using the flag prior on the model parameter, but and the result can be there can be a minor change on this result if I choose a different prior, but the conclusion should not be different because no matter which prior I choose, the Bayesian model selection compares the model and choose one of them. Then I'll show you the result from the model selection using the distribution of delta chi-square, which is the improvement of chi-square by the iterative method. So you can see that the distribution of delta chi-square from two different candidate models shows delta chi-square value lower than the confidence levels in most cases. So the right table shows exactly how many cases show such cases. You can see that when the confidence level is 95%, in 91.6% of cases, both models, lambda C and Pele, are ruled out. And if the confidence level is higher, 99%, it decreases to 79.3%. So, but still, I would say this is a high rate. So in most of the cases, at least for 95% confidence level, 99% confidence level, this model selection method excludes both models, not only lambda CDM but also Pele. And then this model selection can also show that lambda CDM, for this case, lambda CDM is closer to the fiducial model than the Pele model. So you can see other two numbers. So this number shows that about 8.2% of cases for 95 confidence level, lambda CDM model is consistent, but Pele model is not consistent. And if the confidence level is higher, it increases to 19.3%. But for 0 cases, there's no case that lambda CDM is ruled out, but Pele is consistent. So this result shows that lambda CDM for this example, lambda CDM model is closer to the fiducial model than the Pele model, which is consistent with the result from the Bayesian model selection. So this model selection method using the based on the iterative smoothing method can show not only which model is closer to the fiducial model, but also can exclude the all candidate models if none of them is the true model. So this contrast between the two different model selection methods seems remarkable. But before I finish presentation, I need to mention my ongoing work, which is method of iterative smoothing with combined, because this work is important for more practical application to not only model selection, but I have just shown, but also parameter estimation, searching for systemized features, and so on. So right now, I'm preparing reconstructing the expansion history using Taiwanese supernova data and BAO data simultaneously for daily collaboration. So you can see that the reconstructions shows good fit to the both data, and Taiwanese supernova data and BAO data. So I developed a way to reconstruct the expansion history using those two data and show the result and get that kind of reconstruction and with the data. So these two figures shows that the iterative smoothing method for these two data is working well, not only for both data. So I'm preparing this. So this is in preparation, but I hope to show you how it works for these two different data with different natures sooner or later. And I'd like to expand this method for not only these two data, but also for many different kind of data for cosmology. So the results I have shown using the iterative smoothing method in the previous slides are all using only one data, the Taiwanese supernova. But to make it more practical, I need to use the data which is a combination of data sets with different natures. So that's why I'm saying that this ongoing work is important for more practical applications that I shown in the previous slide. So and here's the summary of the second one. So first, conventional Bayesian evidence approach can select the true model if the true model exists among the candidates. If not, it will select merely the least incorrect one. In contrast, normal frequencies approach for model selection using the iterative smoothing method can rule out candidates independent of other models. Since we deal with unknowns in cosmology, this can have important not only practical but also theoretical implementation, especially if it uses the combined data. So, thank you for listening to my talk. For more detail, you can see the papers on the slide or ask questions.